Hello, today we're going to go over the domain of a function. We're going to represent that domain in interval notation. So if you have not watched the video on interval notation, go back and watch it. You don't have to go back and watch it so long as you're familiar with interval notation though. Okay? Let's start off with the definition of domain. So this says that the domain is a set of input values for which the function is defined. Okay, so it's all, a nice easy way to put that is that it's all of our possible x values. The key rules for functions you have studied so far. So what I want you to know is this. Sometimes students get confused when we're finding the domain. When do I know it's all reals? When do I know that there are exceptions? So far, you've learned two rules in the past, maybe more, but these two should stick out. You cannot have 0 in the denominator of a function or a fraction. You cannot have a negative number under a radical. So we're going to look at examples with those today. Now later on when we talk about functions like logarithms, we're going to have additional rules for the domains. But just to get us prepped for what we already know, this is where we are starting out. So our first example here is just a set of ordered pairs that represent a function, and I want to know what are the possible input values if this is our function. So going left or right, let's see, we could have a -3, a -1, 0, 2, and 4. Those are our possible input values for the function in number 1. Fairly simple. We're just writing down the x values. Next one right here. What is the domain for this function? 3x squared plus 2x minus 6. And so this is where some students get a little bit like, I'm not for sure, And so the question is, go back to these two rules right here. It says you cannot have a 0 in the denominator. By that we mean that you can't have something like 7 over 0. Now you can have 7 over, let's say, 5 times 0 plus 1, because this simplifies to 7 over 1. And that's okay. The final value of the denominator is not 0. But here 7 over 0 is an issue. You can never, ever, 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 ever divide by 0. So that's mainly dealing with rational functions, or those fractions. If you got a fraction of function, you should throw up a red flag and say, I better not have the denominator come out to be 0. That's when I've got a domain error. The other one says you cannot have a negative under a radical. Remember, our radicals look like this, and we're talking about square roots here. So you can't have the square root of -5. Yes, I know you might have learned about imaginary numbers, but we're just talking about real numbers. So a radical should throw up a red flag and say, better not be negative. It can be 0, like you can take the square root of 0, that's okay, but it can't be less than 0. So these are the two we're focusing on. We should be keeping an eye out for fractions and keeping an eye out for radicals to make sure that we don't have any domain errors. Now this is just a regular old polynomial. There are no restrictions on the domain. So in this case it's all reals, and writing that out in interval notation is going to look like this. Remember, that's how we write all reals. Once again, if that looks kind of weird to you and you're like, I don't remember learning that, go back and watch my video on interval notation. All right, number 3 right here says the g of x equals 1 over x plus 5. Oh, now we've got something that goes back to these rules. We've got a fraction. What can we not have in the fraction? A 0 for the final value in the denominator. So how do I figure out the domain on this one? Well, I take whatever's in the denominator, and I know that whatever x plus 5 is, it can equal 0. So what value of x will make x plus 5 equal to 0? Let's write it out. X plus 5 equals 0, and solve for x, you get x equals -5. And that makes sense. If I put -5 in, I get 1 over 0, and that's an issue. So let's make sure that x can't equal -5. That's what we need to write out. If we were writing in alligator notation, we'd say all reals except for -5, right? But we can't do that. We want to write it in interval notation. So we're going to start at -infinity and go all the way up to -5. Don't include -5. Jump over it and then go off to infinity. And this is how we write that that x cannot equal negative 5, that's how we write it in interval notation. All right, that's our domain. Let's look at the next one here. F of x is equal to the square root of x plus 5. There it is. So now we've got a radical, okay? And I know that with radicals, I can't take the square root of a negative number. It can be 0 this time, but it can't be negative. So I'm going to take what's underneath the radical. Remember, this little symbol is called the radical. What I wrote in the box right here, that's called the radicand, what's underneath the radical there. The radicand must be bigger than 0 or equal to 0. That's a fancy way of saying it's got to be positive or equal to 0. And now I'm going to solve it for x. So x, subtract 5 from both sides, and x must be greater than or equal to negative 5. You can plug in points when you look at this, like negative 3 is bigger than 5. If I put in negative 3, I get the square root of 2. That's okay. If you put in negative 5, you get negative 5 plus 5 is 0. Yeah, you can take the square root of 0. Pick something on the other side. If I pick negative 6, now negative 6 is less than negative 5, so according to this alligator notation right here, it should give me an error. And negative 6 plus 5 is negative 1. So you end up with the square root of negative 1. Good luck with that, you know, if you're staying in the reals. Can't happen. So we need to write this right here out for our domain. We're going to write it out in interval notation so we get the answer correct. Don't leave it in alligator notation. So we go from small numbers all the way up to the largest number possible. Now this can equal negative 5. So I want something that can be negative 5. So it starts at negative 5 and then goes off to infinity. Now, if you're having a hard time understanding that, let's draw it out on the number line. What I'm saying is right here is negative 5, and we go off that way, and the numbers get bigger. Right here, the numbers get smaller. And I'm saying it can be equal to negative 5 and greater than. Any of these numbers to the right of negative 5 and including negative 5 make this value, the radicand, 0 or positive. Anything this way will make what's underneath this radical negative, and we can't have a negative number. So this is the same thing as saying this right here or this right here, but this is our interval notation, so that's what we want to write it in. So equal to negative 5, that's why we got the bracket. That's where it starts on the left side, goes off to infinity. We never include infinity, so we put parentheses with it. Try out the next one. The f of x is equal to the square root of 4 minus x squared. So once again, our rules for radicals is that they cannot be negative. So I'm going to take what's inside right here and say that 4 minus x squared must be greater than or equal to 0. Now here's a case where it's a lot easier to work this if we factor it because of that square there. So this is a difference of squares. We square root the first term, square root the last term, write it down twice, put a plus with one and a minus with the other, and these two multiply to give you something bigger than or equal to 0. And then we can say 2 plus x is greater than or equal to 0, and 2 minus x is greater than or equal to 0. So x must be greater than or equal to negative 2, and negative x is greater than or equal to negative 2. Divide both sides by negative 1. Remember, when we divide with inequalities, divide or multiply by negative, we flip the sign. And so this is what I get. X is greater than or equal to negative 2, and x is less than or equal to positive 2. So if I'm looking at this on the number line, it looks like this. Here's negative 2, here's positive 2, there's 0 just for reference. They're both solid at negative 2 and 2, and then they connect like this. So to write this out in interval notation, we're going to start at the left at negative 2, and then go all the way up to 2. This is our domain. Let's take a look at some of these. Actually, we'll wait. We'll look at the graphs later. Let's keep on. We've got a few more to look at before we look at it graphically. Try out number 6 right here. Find the domain. So remember, we've got two rules that we're talking about so far. We've got fractions and we've got radicals. Here's a fraction, and the final value in the denominator cannot equal 0. So we're going to say that x cannot equal 0 in this case. That was pretty simple, but it needs to be written in interval notation. So if we're looking at it like this, it goes from negative infinity all the way up to 0, skips over 0 like this. So in interval notation, we're going to say start at negative infinity, go up to 0, do not include 0, then pick back up at 0 and go to positive infinity. And there it is in interval notation. Once again, a fraction, we want to make sure that the denominator does not come out to be 0. So what makes it 0? Set it equal to 0 and solve. Negative 2. So x cannot equal negative 2. That means if this is what we got, then drawing this out, it goes all the way up to negative 2 and then to infinity like that. So if we're writing out the interval notation, we go from negative infinity to negative 2, skip over negative 2, and go to infinity. That's our, oh, you can't see it, can you? That's our interval notation there. All right, two more to look at. Let's look at number 8 here. Number 8 sometimes throws students off because they see two x's, and they say, what's going on with that x in the top? What do I got to worry about there? And really, there's nothing. There's nothing in the top that's going to make the bottom 0, and in this case, there's nothing in the top that has a radical. Notice with the next problem we look at, there is a radical in the top, so it will matter. But this one does not have a radical in it. So it really doesn't matter what's going on up there. This is the important thing. The denominator here cannot equal 0. So what makes the denominator equal to 0? Solve for x, and that's what x cannot equal, negative 4. So writing this in interval notation, it goes from negative infinity to negative 4. It skips over negative 4 and goes to positive infinity. That's the same thing as saying all real numbers except for negative 4. I don't know why that just came back up. Let me turn that off. So anyway, it just want to remind you what I'm talking about, right? Let's look at one more. It's kind of like the music that plays at the end of like the Academy Awards. You know, when somebody's up there talking too long, the music comes on. I think the computer's saying, all right, now's your time. Wrap it up, Mr. Burnett. Not until after I get some more water here. All right. So g of x is equal to the square root of x plus 2 over x minus 1. What's going on with this? So two things. First one is the x minus 1 in the bottom. It cannot equal 0 because if the bottom's 0, we got those issues. So let's tackle that first. So x minus 1 equals 0 when x equals 1. So that's one thing we've got going on. X cannot equal 1. But we also have to pay attention because there is a radical up here. Whatever's underneath the radical cannot be negative. So x plus 2 must be greater than or equal to 0. And so subtract 2 from both sides, and it says that x must be greater than or equal to negative 2. And so if I write this out on a number line, right here is negative 3, negative 2, negative 1, 0, 1, 2, 3, and so forth. What is all this saying? For 1, we have to be bigger than negative 2. It can be equal to negative 2. That's fine. And it goes this way. But it cannot equal 1, so we have to throw that out. So that's what I'm looking at here. And now I got to put that in interval notation. So I have to include both restrictions here. Because if I didn't, if I said, you know what, top says it's got to be bigger than negative 2, well, if I put 1 in the top, that's okay, I get root 3. But if I put 1 in the bottom, I get 0. And then that gives me an issue. Likewise, I can't just put, say, okay, everything but 1, because negative 3 wouldn't make the bottom 0, but it would make the top have the root of a negative number. So this is what it's got to be, the union between the two. So I'm going to start at negative 2, include it, go all the way up to 1, skip over 1. We're not including the 1. Don't forget you can put that u in between if you're answering the homework. And then go to infinity. All right? There's your domain for that one. Now, that's all I've got for solving algebraically for you. But I would like to take you through the graphs of these. So switch over to Desmos, and we're going to put some of the stuff in on graphs. Okay, so you've been taking notes, right? Let me gather up my notes. Let's pick up at number 4 here. My computer. There we go. Number 4 is what we want to look at, and I'm going to type in f of x equals the square root of 5. X plus 5. There we go. And what we got before for that domain, take a look at it. We got this right here, that it starts at negative 5 and goes off to infinity. Now look at the graph. Nope, that's not the graph. That's the math teacher, right? Look at the graph. It says the square root of x plus 5, and then over here, let's see if you can follow my mouse, it starts right here at negative 5, it includes that, and it goes off to infinity. So those two match up. Look at the next one. It says 4 minus x squared. So 4 minus x squared looks like this. It's like the top of a circle. Now, what did we get for our domain here? We got from negative 2 to 2, and we're including those. And if we look at the graph, all the possible x values here, they go from negative 2 to 2 and nothing on either side there. All right. Let's look at the next one. Number 6, we said that was the g of x equals 1 over x. Let's write that out. So the g of x is equal to 1 divided by x. And we'll turn off that green function there. So notice what's going on right here. Our domain, we said, was everything but 0. So it's like, when we write it out like this, it's like that's saying all reals, right? And then that's saying exclude 0. So if I look at the graph here, we don't have a value at 0. In fact, if we typed in like the g of 1, if I want to evaluate this at 1, the g of 1 is 1. Do you see the output right here? Using our function notation. The g of negative 3 is negative 1/3. But if I type in that 0, it says undefined because there is no value. There's a vertical asymptote right there when x's value is 0. So it's not part of the domain, and that's what we got on that one. Let's look at the next one. Number 7, we had an x plus 2 in the bottom. And we called it the f of x. It doesn't really matter. I'm going to leave it g of x because we've already defined f of x up here. Notice x plus 2, all it did to the graph was shift it to the left 2. That's just a transformation. And now negative 2 is where that vertical asymptote is. And look at what we got for our domain here. It includes everything but negative 2. I'm telling you, when you do your homework, you can't use the graphing calculator on your quiz or test, but if you use it to help you understand like what's going on with this domain, or even to check your homework, it's a great way to look these things over, and you'll get more and more used to what these graphs should look like, and then that's when you're on your way to really getting ready for calculus. Okay, let's look at our next one here. We had on number 8, 3x over x plus 4. Let's go through and type that in. 3x over x plus 4. So I'm going to change that to a 4. And we've got 3 times x. And so let's zoom out so we can see what's going on a little bit easier. It looks like we should have a vertical asymptote maybe at negative 5. But I think if we zoom out further, this is a case where it might be kind of hard to see on the graph. But we can still check our answer. We said negative 4 is what we were excluding, so let's put that in, and notice it says it's undefined. So we can also graph a line, x equals negative 4, and you can even, like in math class, you normally make that like a dashed line, right? So you can make that a dashed line, and you can see how that right there is the vertical asymptote for that rational function. All right, number 9. Number 9 was the fun one. We had a square root in a fraction, right? So let's see what number 9 looked like. It was the square root of x plus 2 over x minus 1. So let's type that in. The square root, SQRT, of x plus 2 over x minus 1. And this is what this weird thing looks like, right? Now, what did we say the domain was? We said it starts at -2 and includes it. It skips over 1 and then goes to infinity. So going back to the screen right here, notice it starts at -2, includes it, and it skips over 1. We're kind of zoomed out here still, so let's zoom in. And we can see that it's going to skip over 1 and then go to infinity. Let's see. I believe that was all of them. Yep, that was the fun one at the end there. So hopefully, like I said, as you go through these and try them out, take time every once in a while to stop and graph it. If you can do it every time, that's great. Or at the very worst, do it on a few of them. But learn how to graph them in Desmos, learn how to check it, because you're going to get better and better and more comfortable with all these weird graphs that before you're like, I'm a little nervous doing this, let's just punch it in the calculator. I want you to try it first without looking at the graph. You can use the graph to check it, and eventually when we start graphing these things by hand, you're going to be very comfortable with it, and you're just going to be rocking right through these. Okay? Try out the homework. Thank you for watching the video. Let me know if you have any questions, and keep working hard.